Rubber band stiffness. If we change the thickness of a rubber band, how does it change oscillation? Observations. First, we were interested in the way temperature affected elasticity. Then decided we were more interested in how thickness and stiffness affected elasticity. Questions. How does the stiffness of the band affect oscillation? Hypothesis. If we add more strips of rubber band each time, then the amount of oscillations per second will go up exponentially. Because the more rubber bands means the more stiffness, which means the more force acting on the weight. Variable. Independent. How many strips of rubber bands were attached? Dependent. Amount of oscillations per second. Constant. Weight and dropping point. Materials. 3 rubber bands cut into 5 equal strips. 1 500 gram weight. Red stiff copper wiring type. 1 stopwatch and 1 table clamp. Procedure. 1. 5 3-inch rubber band strips. 2. Attach rubber band to 500 kilogram weight. 3. Raise band until the rubber band is limp. 4. Let go of the weight and count the number of bounces until your partner tells you the time is up. 5. Divide the number of oscillations you counted by the second you counted. Repeat steps 1 and 5, adding another strip to the weight each time. So this is a picture of a procedure, and right here is our 5 strips of rubber bands, and that's our 500 kilogram weight. Pay attention to that, and not to that. Data table. Strips of rubber band and oscillations per second. So with the first strip of rubber band, it oscillated 1.6 times. With the second strip of rubber band, it oscillated 2 times. With 3 strips of rubber band, it oscillated 3 times. With 4 strips of rubber band, it oscillated 3.5 times. With 5 strips of rubber band, it oscillated 4.333 times. Graph. So this ended up being a linear trend, which was kind of surprising to us, but at the same time it kind of wasn't, because our hypothesis said it would go up exponentially, and ended up not going up exponentially. So that was kind of really interesting, but yes, I'll get more into that later. Analysis. We let the weight bounce for a certain amount of time. We then divided the number of oscillations we counted by the number of seconds we counted. For example, so we had a weight and it oscillated 13 times, then we divided by that 13 by 3 seconds, which ended up getting 4.33. And we did that pretty much for each one, except for some of them 3 seconds was way too much. So we had to do it less. And yeah, and then it ended up being 5R equals 4.3 oscillations per second. From right, this would be called hertz, so it would be 4.33 hertz. So we also calculated the spring consistency of a rubber band. And how we did that was we pulled the rubber band farthest we could apart, and then we let that go, and then we see, and then we would, so we pulled it the farthest we could put apart, and then put one of those spring scales on it, and see how much mass, how much weight would be on the rubber band, and that would be the consistency of the rubber band. Conclusion. Our original hypothesis that if we added more strips of rubber bands, increasing the stiffness, the amount of oscillations would most likely go up exponentially. Our data supported our initial idea that oscillations would increase, but not exponentially. Our data increased at a linear trend, which I just said earlier about the graph. As you can see, linear. So error analysis. One of our strips was slightly longer than the rest. We did different amounts of second consisting each time. We weren't always sure how many times the weight oscillated, and sometimes we would have to run up or down, because after going up and down, it kind of goes side to side, and we didn't know if to count that as a up and down or as a shake. We weren't always exactly on time with the timing either. Extensions. How does it affect the sound of a string instrument? Does it sound better the stiffer it is, or the more elastic it is? Group members. I created the rubber bands and setting up the experiment, and Sage did the calculations on the PowerPoint. Thank you very much.